Good morning, friends. Welcome to Water Resources Engineering class. We are dealing with Unit 5, mainly deals with the canals, canal design, waterlogging, canal lining, drainage in canals, drainage in the irrigation fields because of the water that is coming through canals. So all these aspects we are studying in the 5th unit. So this all we have completed classification of canals and different based on different parameters, maybe alignment. This is what we have done it. But today's lecture we focus on what are the drawbacks of Kennedy's theory. We have studied Kennedy's theory. We have done some problems on Kennedy's theory. But what are the drawbacks in that Kennedy's theory? And what is the next theory? The next theory is Lacey's theory. Kennedy's theory and Lacey's theory both are the silt theories which are utilized for design of channels in alluvial soils. Coming to the drawbacks of Kennedy's theory, first one is he started with assuming D value and then solving it. But at a later stage, he introduced B by D ratio also in the problems. But thing is, he is not able to explain the B by D ratio importance significantly. Because B by D ratio is very important parameter for the stable channel design. But how it influences that he could not really explain. That is his first drawback. Second thing is only average regime conditions are considered. That means he did not ensure the complete stability of the channel against silting and scouring. That is number 2. Third one is oversimplification of sediment properties. The entire sediment property he has taken is only the critical velocity ratio. That is the only thing through which he explained the entire theory. So that is basically to what extent that validity is there is a question. Then he never talked about the gradation. That means what are the different gradations of the silt, the particle sizes of the silt. He did not talk anything. And second thing is, how much is the quantity of the silt that is being carried in the channel? The quantity, that is what we call it as charge, silt charge. Then the gradation, that what you call it as silt grade, both are not really explained by him. That is next 4th one. He never explained any slope equation. Because most of his theories are only straight away critical velocity he has taken. From that only he has taken the whole thing. So no slope equation he has given it. Whereas slope is longitudinal slope is a very, very important parameter in the channel design. Then the entire Kennedy's theory is depend on only 2 equations. One is a critical velocity ratio equation, basically that is velocity equation. And second one is again velocity equation, that is Cutter's equation. So whatever the limitations are there in Cutter's equation, all those limitations are now introduced into Kennedy's theory. That is one of the biggest disadvantage of Kennedy's theory. And moreover, this entire approach, whether it is a trial value assuming it, so it's all trial and error procedure. That is one thing actually which is more cumbersome actually to do it also. And last one is restricted regional applicability, because most of the Kennedy's observations are only in Punjab. Only thing is with just that M value, that is critical velocity ratio, he tried to give the what you call it as for any region, but Kennedy's theory is mainly restricted to the regional applicability. So these are the 8 drawbacks of Kennedy's theory. And how Lacey has addressed some of these problems, right, in his theory, that which we will take it up actually. So Lacey's theory, This is the next popular theory as far as design of channels is concerned in alluvial soils. Lacey is basically a British engineer, but most of his works are in UP. He has done it. He developed a theory in 1930 for the design of channels in alluvial soil. Unlike Kennedy's theory, which relied on velocity-silt balance, Lacey considered the regime concept. That is the first difference. A condition where the channel is stable. Regime condition means the condition is such that the channel is stable. The channel is stable in the sense that it is neither silting nor scouring. Neither silting means the silt is transported along with the water in the canal. Nor silting means silt is not deposited actually, right? Nor scouring. Scouring means the velocity is not so high such it what erodes the bed and the banks actually. So he defined for this non-silting, non-scouring basic thing for channel, he has given a regime concept actually. So what is a regime channel? A regime channel, it is a stable channel. First thing, a regime channel means transporting a regime silt charge. Charge means quantity. Please remember, silt charge means silt quantity. A channel will be in regime if it flows in unlimited incoherent alluvium of the same character as that transported and the silt grade and silt charge are constant. I will explain these points. A channel is said to be in regime when it flows through unlimited incoherent alluvium. What do you mean by incoherent alluvium? Incoherent alluvium means the soil is composed of loose graded material. That is the first thing. The soil is considered actually very loose actually. The channel which is passing through such a soil, the soil is a very loose granular graded material which can be scoured with the same ease with which it is deposited, because this soil can be easily scoured actually. So that is what we mean by incoherent alluvium. Then what is you mean by regime silt charge? Regime silt charge means the load. Charge means the quantity. So it is the minimum transported load consistent with fully active bed. So that means how much is the quantity of the silt that is being transported in the channel. That is what we call it as silt charge. What is silt grade? It indicates the gradation between the small and big particles of the silt. So three things are there. Channel is passing through an unlimited incoherent alluvium and it carries actually regime silt charge and silt grade. Both are constant. That is the next thing. That is what Lacey has mentioned as a regime channel. What do you mean by regime conditions? A same thing I explained number of times. What do you mean by regime conditions? First thing is what? The channel is flowing through unlimited incoherent alluvium. That is the first thing. Then second thing what? Silt grade and silt charge are constant. Third thing is discharge are constant. If these three conditions are satisfied, then actually we say that the channel is a regime channel. The channel condition is in true regime. That is what this first talks about. Then will it attain true regime immediately the moment water flows in the canal? Immediately the canal attains true regime? No. First it attains the initial regime and then final regime. What is the difference between initial regime and final regime? Initial regime means the channel shape is formed. Channel shape is formed, but the slope is not yet formed actually, not yet finalized. Slope is still undergoing, the bed slope of the channel is still undergoing changes. When once the water flows, the shape first takes a change and then the slope takes a change, right? Because it is not a lined canal, it is a channel passing through alluvial soil. Therefore, first thing is channel has formed its own section, fine, then but slope is not yet formed. That is what we call it as initial regime. What is final regime? Final regime means both it's a shape, that shape means I mean by section. Section means the sizes, bed width, side slopes, everything. So the channel after attaining its section and longitudinal slope both is said to be final regime. What do you mean by permanent regime? There is only one section and one slope at which the channel will carry a particular discharge. That is what we are doing in the design actually, right? With a particular silt grade. Silt particle sizes are also only same sizes actually. Then natural silt transporting channels have tendency, generally the silt transporting channels, unlined canals passing through alluvial soils assume a semi-elliptical section. That is there. Lacey assumed that slowly actually any unlined channel passing through alluvial soil attains a semi-elliptical section. That is first thing is there. That semi-elliptical section may be in such a way that it is what we call it as more wide actually at some points and or more deep, making it into a semicircle depending upon the sizes or depending upon the silt gradation. Lacey observed that in regime channels, the silt carried by the river is in equilibrium with the transporting power of the flow. Channel dimensions are self-adjusting. The bed width, the depth, the slope and velocity are self-adjusting to achieve stability. The channel tends to form a semicircular section in the regime conditions. Semicircular, semi-elliptical, almost the only thing is that depends on the section dimensions. Then assumptions of Lacey's theory. Channel is an alluvial soil, right? Bed material is same as that of silt being carried. That means from the river, whatever the water that flows into the canal, that also carries some silt along with it. The silt character is same as the channel bed and banks material character. So that is first thing, because the whatever the silt transported is basically the moment it deposited, it becomes alluvial soil. So that's why the channel whatever you are now designing is also in the alluvial soil. So that's why the bed material is same as the silt being carried. That is first thing. The channel is flowing in a regime state. That means no silting, no scouring in the channel. And then silt is uniformly distributed. So that means the whatever silt that is transported, it is uniformly distributed, and transport of that silt is continuous process. The velocity of flow depends on mainly the silt factor. Please remember, previously Kennedy's theory, velocity depends on what actually? Critical velocity ratio. That's what Kennedy defined actually. Then Lacey's theory, the velocity depends mainly on silt factor, and the silt factor is a function of the diameter of the silt particle. Lacey proposed, four equations for solving or for designing a channel in alluvial soil. So he has given his own equations. He has derived these equations, but we take these equations and use it for solving the problems related to design of channels. So what is the first thing? He has made, because already he mentioned the velocity depends on the silt factor. We know that already velocity depends on basically the discharge and velocity are interrelated through continuity equation. So he brought into picture the third parameter, right? The silt factor, and the silt factor and velocity are related. That is the first equation he has given. That is thing. What is that relation? So that relation is this. V is equal to QF square by 140 whole to the power of 1 by 6. And here what is V is mean velocity, F is the silt factor, and then the what is other, that's all. But silt factor, which depends on what? The size of the silt particle. The size of the silt particle, if it is known, then it can be, silt factor can be calculated. F is equal to 1.76 root of m. What is this? M is the dia of silt particle. Right? Once this is found out, then by using this equation, because normally when you are designing a channel, you are given with the discharge and you are given with the diameter of the silt particle or silt factor. So knowing the Q and F, you can calculate V. And there is another relation he has given. What is the relation between the discharge and the wetted perimeter? Perimeter and discharge, excellent equation actually, which is used in the design of most of the irrigation structures. So that relation is wetted parameter is equal to 4.75 into root Q. Very pop, because most of our designs are based such that because there cannot be any soil for construction, which is almost, I can say this soil is loose soil through which we are designing everything. So that's why he has taken P is equal to 4.75 root Q. That is second equation actually. Knowing these two, he has found out what is the equation for regime hydraulic radius. Rather than regime hydraulic radius, this is more popular as regime's cover depth. The regime's cover depth principle is used mainly in the design of the diversion headworks such as weirs, barrages. But as far as the canal is concerned, we restrict ourselves that this R is equal to regime hydraulic radius. Previously, we used to calculate R is equal to A by P. But from the same thing, actually, Lacey has given one more empirical equation like this. That is 5 by 2 into V square by F. So, this is the third equation. And fourth equation Lacey has given is, he has given one equation exclusively for slope. So these are the four main equations for the design of channels. What are that? First one is discharge, velocity, silt factor. That is first thing. And silt factor depends on the diameter of the silt particle. The second one is wetted parameter, discharge. Third one is the velocity, silt factor and hydraulic radius. Last one is again that depends on discharge, silt factor, that is slope. So that means if what are the things that is need to be given to you if you want to design an irrigation channel by Lacey's theory, if discharge is given and silt factor is given, if these two are given, then the entire channel design you can make it. You can see it in the slope equation QF, in the velocity equation QF, in this perimeter equation only Q, in the basically the hydraulic radius equation velocity, silt factor. So the whole thing revolves around discharge and silt factor are known. We can design the channel using Lacey's theory. And regime velocity equation, this is also same basically whatever we have previously done it. Explanation. For a given discharge Q and bed material, that is through silt factor, Lacey's equations provide the stable channel dimensions with depth, slope, velocity and perimeter. Unlike Kennedy's theory, which is trial and error, there is no slope equation, Lacey gave direct formulae for all the parameters. The design ensures that channel can carry discharge without silting and scouring. So it is a regime channel. In summary, the Lacey's theory is a regime theory for the design of stable irrigation channels in alluvial soils. It is based on the discharge and bed material properties and provides direct formulae for velocity, slope, hydraulic radius and perimeter, making it more comprehensive compared to Kennedy's theory. Again, what are the things? Just let me explain before taking up a problem by using Lacey's theory. First, calculate silt factor. If not given, either silt factor should be given or you should be given with the particle size. Whatever it is, based on that, first one is silt factor should be known to us. Second one is calculate velocity of flow QF square divided by 140 whole to the power of 1 by 6. Then calculate area of flow. Then you know P is equal to 4.75 root Q. A is known, P is known, but A and P are known. Can't you calculate what is B and D? That is next thing, because normally the channels are only the trapezoidal channels. So if you take the trapezoidal channels, B and D depth and the side slopes are z horizontal to 1 vertical, then A is equal to BD plus 0.5 D square and P is equal to B plus D root 5. Yesterday we have done many problems on this. Then calculate R is equal to 5 by 2 V square by F, and R also you can check with B and D whatever you have calculated using A by P and check. Naturally both should be similar. Then find the slope finally. This is the basic steps that which we have to follow in Lacey's theory. With this, this lecture is completed and we will take up problems in the next lecture. Thank you so much.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.